Good morning, everyone. Welcome to the first lecture of organic chemistry in our incredible crash course. And in this lecture, we'll be covering IUPAC nomenclature from a very basic level to a decent level at J mains or NEET level, and probably even J advanced. But the current question is who should watch this lecture? So my answer to that is you can watch this at every stage of your preparation, but it's preferable if you have done the chapter a couple times before. But if you're running less on time and you need a quick brush up of this chapter, then this video is perfect for you. So without further ado, let's begin. So, IUPAC, the International Union of Practical and Applied Chemistry, in which they make all the rules for chemistry, and we have been forced to follow them. So, let's begin. Hydrocarbons refer to compounds which contain only hydrogen and carbon. For example, your butane, C4H10, your CH3, no, sorry, CH4 methane, or probably C2H6. Anything which has only hydrogen and carbon is referred to as a hydrocarbon. And organic compound is something which have hydrocarbon. I mean, this is basically hydrocarbons is a subset of organic compounds, and basically this also contains compounds like C5H5N, which have carbon and hydrogen along with an extra atom from another group, which isn't carbon or hydrogen, and this is what we call organic compound. Now, if we think about saturation and unsaturation, you must know that alkanes are unsaturated. Alkanes are saturated. Alkenes and alkynes are unsaturated. So, basically, if you see in any compound, you see a carbon-carbon multiple bond, you can call it unsaturated. For example, this is an unsaturated compound because it contains a carbon-carbon unsaturated bond. But this is a saturated compound because the double bond here is not between a carbon and carbon, it's between carbon and oxygen. Hence, we are not considering this an unsaturated compound. Now, let's learn about cyclics. This is what we call homocyclic. Anything in which the ring is comprised of only one atom, which in most cases is obviously carbon. But this is also homocyclic compound because the oxygen atom which is attached to the ring isn't a direct part of the ring. These are all still carbon atoms, hence we call them homocyclic. But this is a heterocyclic compound because suddenly here nitrogen is a part of the main six members of the ring, and this is what we call heterocyclic compound. Now, aliphatic compounds are those compounds which are non-aromatic. Just remember this definition for now. We will cover what non-aromatic means in general organic chemistry. But for now, you can think of aromatic as something which looks like this, where there is alternating single and double bonds across an entire ring. And there are exactly 4n plus 2 pi electrons, like one bond, one extra pi bond corresponds to 2 electrons. So if the total number of pi electrons in the entire cyclic conjugation of the ring is 2 more than a multiple of 4, or in mathematical terms we can say 4n plus 2 pi electrons, then that compound is called to be aromatic. There are of course more rules and nuances related to aromatic compounds, but for now this is all you need to know. Alicyclic compounds are cyclic compounds which are not aromatic. For example, this right here, there is alternating double and single bonds, but it does not cover the entire cyclic compound. So this is what we call a non-aromatic compound, and it is called alicyclic, which are cyclic. They have a ring, but they are non-aromatic. So that's what we call alicyclic. Now I expect you to know what degrees are. Degrees is basically, do I need to explain you that? But see, if any carbon atom is joined to two more, it's called 2 degree. If it's a terminal or joined to only one more carbon atom, it's called 1 degree. And if it's joined to like 3 carbon atoms, this is called 3 degree. And say for example in like neopentane, it's joined to 4 carbon atoms and it's called 4 degree or quaternary. Okay. Now these are types of double bonds. Conjugate double bonds are again that alteration of double and single bonds is called conjugation, like one double, one single, one double. Cumulative double bonds are double bonds which are directly next to each other, and basically one carbon is forming two double bonds on two sides. And isolate double bonds are those which show no actual relation with each other. They are not cumulative and they are not conjugated. So that is what we call isolated. You can see these two double bonds are not related to each other, so we call them isolated from each other. Okay. Now, if we talk about special names we give to positions, then the carbon atom which is right adjacent to a 6 carbon ring, like this exact ring that we call a benzylic carbon. If a carbon atom is adjacent to a double bond, it is not a part of the double bond, but it is adjacent to the carbon which is a part of the double bond, we call it an allylic position. And if the carbon atoms are directly adjacent to a triple bond, we call it the propargylic position. Degree of unsaturation is a measure of how many less pairs of hydrogen are there corresponding to the compared to the corresponding alkane. For example, this is a carbon chain with 3 atoms. The formula for this will be, actually there are 2 bonds here, so this will be 2 hydrogen here, 2 hydrogen here, because carbon can only form 4 bonds in neutral state. And this compound in total has 6 hydrogen. Okay, but actual propane, if you see, has the formula C3H8, but this with the same number of carbon atoms has a formula of C3H6. So you can see there is one less pair of hydrogen, which means there are 2 hydrogen less here compared to the parent alkane from which this compound was maybe prepared. Or basically the same number of carbon atoms in an alkane would have 8 hydrogen, but this only has 6. So we call this to be unsaturated with a degree of unsaturation equal to 1, because its number of hydrogen pairs less as compared to its parent alkane is only 1. The number of hydrogen atoms less is 2 and number of pairs is 1. That should be easy to comprehend. And this is a direct formula for the degree of unsaturation. You take the total number of carbon atoms and subtract this quantity from it, and this quantity is given as number of nitrogen plus number of hydrogen minus number of halogens minus 2 whole divided by 2. A way to remember this is nu, her or him, depending on your gender or sexuality, nu, her or him, x, 2, gone. Gone in the sense this is subtracted from the number of carbon. Nu, her, x, 2, gone. Okay, basically you have moved on from somebody. And yeah, and just so you know, an extra point they can ask as an MCQ, halogen is treated as hydrogen in while counting degree of unsaturation. And basically what this means is, if you have a compound like this also has 2 less hydrogen compared to its parent alkane, because the two hydrogens has been substituted by 2 halogens. But still we will call it fully saturated, because halogens are treated as hydrogens while accounting for the degree of unsaturation. Okay. Read this if you must. Now I want you to remember a couple priority orders. What priority orders? Functional groups are given the maximum priority, and we will like to take the maximum number of them while selecting the main chain. What is main chain? Main chain is basically, if you have a compound, the main chain is basically the parent chain from which, with respect to which, the other substituents or the other components of the compound will be named. For example, we will have a main chain like this, and other substituents will be here, and we will add them separately as a prefix. But the main chain is the root of the entire compound, and we need to be very careful when selecting the main chain. So these are some guidelines in order to how to select the main chain, and we will go into more depth later. But for now, remember this order: priority to maximum number of functional groups, followed by maximum double bonds or triple bonds, followed by maximum number of carbon atoms, followed by maximum number of substituents, followed by lowest set of positions. For example, if there are basically 2 ways of numbering, okay, say one of them gives the position of a substituent of the carbon chain as 1 comma 2 comma 4, which means at the first, second and fourth position there is a substituent, and when we read from the opposite way it gives us 1 comma 3 comma 4. So this is not appreciated. We will take this one because this set is lower than this. How do we compare sets? We look at the first element. If it's same, we move on to the second one. Since this is lesser than 3, we take it like this. A practical example of this is butane. Basically, chlorobutane. Now there are two ways of naming this compound. You can see these are the exact same compound, but here, if I start numbering from here, okay, you can see this gives me chloro at the second position, but if I start from the opposite side, this gives me chloro at the third position. So I will not take this numbering, I will take this numbering because it gives a lower value of set. Basically this is called a locant to my substituent, and this is what we call LSO or lowest set of. And if all of this is same in all the chains, then we will give the priority to the chain which allows for better alphabetical order arrangement. We will see alphabetical order later. Now if you see order of numbering, the numbering will be decided along what was the word, with respect to the numbering will be decided with respect to the lowest set of functional group, then the lowest set of carbon-carbon multiple bond, then lowest set of substituents, and lastly the alphabetical order. So this exact thing I told you about the numbering thing. First you will check the lowest set of functional group. Functional groups are special groups which can affect the chemical properties of a compound drastically, and we will learn about what the basic functional groups are and their names. Basically you have to give priority to the functional groups, then followed by the multiple bonds, followed by the substituents, and lastly if everything fails, alphabetical order is your last priority. Okay, and yes, as I told you, this is decreasing priority. Here also you can see functional group had the maximum priority. And now we will start actually naming the compound. This is the sequence of name, how a basic organic name looks like. There is going to be a root word, there will be two suffixes, and there will be two prefixes. Okay, ignore that. Yeah, so what is the 2-degree prefix? The 2-degree prefix will be the name of substituents in alphabetical order with their positions. We will see how this works. 1-degree prefix is not that important, it is only used for cyclic compounds, and the basic 1-degree prefixes are cyclo, bi or tricyclo, spiro, and bispiro. Root is basically it's the number of carbon atoms in the parent chain. 1-degree suffix is for multiplicity. For example, if the parent chain only has multiple bonds, so we use ene, ine, triene, enine to show the position of those double bonds. There are of course more more suffixes, but these are basic ones. And 2-degree suffix is used for functional group. Okay. Now sometimes if this is our main chain, the substituent groups, they are also complex. For example, they sometimes need their own numbering. So we can show the substituents of the substituents. So if we want to number our substituent groups, then we always start numbering from the radical carbon irrespective of the priority order. What does this mean? For example, let's say this is our main chain and this is a substituent. So we'll always start numbering from the carbon which is directly attached to the main chain. You can see here numbers are written. Here 1 is starting from the carbon which is the main chain, 2, 3. Okay, and this is called the radical carbon. For example, here you say we learned that we have to give the lowest set of priority to the carbon-carbon multiple bond. For example, if I say let's ignore this main chain for now and let's just look at this compound. Okay, so if this compound you had to name, you would start numbering from here and you would call it propene. Okay, but you are instead violating that rule and starting numbering from here because the substituent starts from this carbon. Like this is the carbon which is attached to the main chain and hence we call it a radical carbon. Okay, Now these are prefixes. Basically, if an alkane is a substituent like this, we call it an alkyl group. If this is a substituent, we call it an alkenyl group. And if an alkyne is a substituent, we call it an alkynyl group. And say the alkyl group is bound to the main chain with a double bond, then we call it alkylidene. If the alkene substituent is bound with a double bond with the main chain, we call it an alkenylidene. And if the same thing is done by an alkyne substituent, we call it alkynylidene. Let's see an example. This is a methyl group. I expect you to know the meth, eth, prob, but, pent, hex, hept, oct, non, and dec counting, which is basically Greek or Latin for the counting of numbers, and we use those to represent the number of carbon atoms. So since there's only one carbon here as a substituent, like this is not negative charge. This means that maybe there has to be a main chain and this is bound to it, and this is the substituent part. So this is what the substituent part is, and this is you bound using this bond to the main chain. So if this is bound to the main chain using this bond, we call it an ethyl substituent. And as I told you, the numbering starts from the carbon which is directly attached to the main chain. So here we start numbering, and this substituent in totality is called 2-chloroethyl, because this is a normal ethyl, but in this ethyl we have added a chloro group. So what happens, we start numbering from here, and chlorine comes at the second carbon, so we call 2-chloroethyl. Okay, this is a special name. Remember, this is called isopropyl. This is called isobutyl. This is called tert-butyl. This basically just means there's carbon and there's 3 methyl groups like this. This is tert-butyl. This is how you write methyl thrice. This is a vinyl group. Remember, this is not attached to the main chain. This is a carbon-carbon double bond inside the substituent. Hence, we still use the -yl prefix and not -ylidene. This is an allyl, where, if you remember, we learned here, this is called the allylic position. And if that allyl carbon just so happens to be the substituent, the radical carbon, then we call this entire substituent the allyl substituent. And similarly, this is the sorry. Similarly, this is called the propyl substituent. I hit my hand and this just went. Sorry. This is what we call the propyl substituent, and the actual IUPAC name, like this is a common name, the actual IUPAC name would be prop2-inyl. Why? Because we start numbering from here, and the second position is the start of the triple bond. Okay. Similarly, it's easy for you now to see why this is called this. So let's move on. Now let's see the dene wale. Okay. The dene ones are the one which are connected to the main chain via a double bond. So this is a methyl group, but it's bond with a double bond. So we change its names to methylidene. This is ethylidene. This is isopropylidene, and this is vinylidene. Now you say it's called vinylidene. Here it was only vinyl because the double bond was inside the substituent, but here the double bond is inside the substituent and an extra double bond with connected to the main chain. So this is also an example of a cumulated double bond, and we call this vinylidene or ethenylidene because this is ethene and connected to main chain via double bond, so ylidene is added. Similarly, this is alylidene, or IUPAC wise prop2-enylidene, and this is propar-gylidene. Okay. Now these are some common substituents you must know. We call this fluoro, chloro, bromo, iodo, these halogens. If the alkyl group is joined via an oxygen atom to the main chain, we call this alkoxy. So this is methoxy, ethoxy, and phenoxy. Phenoxy is nothing but a benzene ring as a substituent to the main chain. This is phenyl, and if again oxygen atom is added in between, we call it phenoxy. Okay. This is called nitro. If only NO is there, it's nitro. So NO2 means nitro. Only NO, nitro. So As I told you, this is phenyl. If there's a carbon atom in between, we call it benzyl. If the carbon atom is joined via a double bond, we call it benzylidene. If it's joined via a triple bond, we call it benzylidine. See how this E changes to Y. It's called benzylidine. Okay. And yeah, credit to Neeraj Saini sir, from which I have personally studied this chapter, and I have used his notes to relay the information to you. So thank you, Neeraj Saini sir, for making this possible. You are one of biggest inspiration for me. So now let's learn about simple substituents and complex substituents. What are simple substituents? Simple substituents are nothing but straight chain alkane groups as substituents. For example, we learnt methyl and ethyl. These are simple substituents because you only need to do like 2 methyl propane. Okay, like propane is the root word and the 2 degrees of prefix is 2 methyl. Sorry, yeah, 2 methyl. As I told you, 2 degree prefix has name of substituent methyl in alphabetical order with position. This is the position. So you have to specify 2 methyl propane. You also need to know how to draw structures from the name. So how do you see? This is propane. So there must be a 3 carbon chain as the main chain, and at the second position there has to be a methyl group. Okay, so this is 2 methyl propane, and this is propane is the root word. 2 methyl is the 2 degree prefix, which is the name of substituent along with the position. Okay. Now, a complex substituent is something which we have to basically, these are not simple straight chain alkyl groups. For example, this substituent, you would have to start numbering them, and you would have to specify that at which position the complexity begins. For example, if this is attached to a main chain, like to a propane, second carbon of propane chain, you would have to say 2 bracket 1 chloroethyl, like this thing, 1 chloroethyl propane. Why so? Because suddenly this is now a complex substituent, because at its first carbon there is extra branching. This is not a straight chain alkyl group. There is extra branching, and hence it's a complex substituent which we will have to put in brackets while naming the compound. Okay, again this is simple, but this is complex. See, this is simple because straight chain, but this is complex because extra branching has occurred. So again you would have to say alphabetical order now. B comes before I. Okay, so since B comes before I, you have to write bromo earlier than iodo while naming this substituent, but numbering by default takes place from the radical carbon as we talked earlier. Okay, and again while attaching it to a main chain, write its name using this complex substituent in parentheses or brackets. Okay, now let's learn about the concept of iso and neo. These are straight chain alkanes like N-butane. N means straight. N-butane ekdam straight. N-pentane straight. N-hexane straight 6 carbon atoms. And octane straight 8 carbon atoms. But if branching takes place at the second to the terminal carbon, for example at the second last carbon, like this is last carbon and second last carbon, branching takes place, and see there are 5 carbon atoms still, so it's still a pentane, but since branching occurred at the second last carbon, we will now call it isopentane. This group is the identification of an isopentane compound, and this entire thing which I'm telling you is valid for number of carbons less than 6. Okay, hence we haven't drawn any octane here because that's 8 carbons. But see, similarly this is isopentane because this group is there and a straight chain follows. Again this group is there and a straight chain follows of 4 carbons, and this group is there. So this is isohexane, total 6 carbons. Neo is the same thing, but instead of a single branch there are now 2 branches. Like this was the second last carbon, and now suddenly there are 2 branches now. So 5 carbons are there. This is called pentane but neopentane, and this is called hexane because neohexane, because again at second last carbon 2 extra branches have been added. But above 6 carbon atoms, the use of neo becomes very obsolete, because say this is like neoheptane. The name is technically correct, but it's very weird to call it neoheptane. I don't know, scientists don't like it, so we just call it 2,2 dimethyl pentane. Actually, yeah, if the same substituent is present on more than one places, you write it like this, but we'll get to that later. And yeah, there is an exception to this entire thing. Isooctane has the iso group, but at the second last terminal carbon, a neo group is also there. So how to remember this? At one position there is a neo thing, and at the other end position there is an iso thing. So this is the structure of isooctane. Remember it. They have asked this before and they will again. Now let's look at concept of sec and tert. Sec is nothing but secondary or corresponds to 2 degree. Tert is nothing but corresponds to 3 degree. Okay. Yeah. For example, this is secondary because this carbon is joined to the main chain, which is a 2 degree carbon, and tertiary means this is joined to the main chain and this is a 3 degree carbon. Okay, so that was it, and let's learn how to use alphabetical order properly. These are considered in alphabetical order. What are considered? Iso is there, then it's considered. Neo is there, then I and N are considered. If there are complex substituents, like as we talked here, complex substituents, then for them we will count di, tri, tetra as complex. Sorry, in alphabetical order. But if they are for simple substituents, we do not count this. Why so? Because in complex substituents, the di will be under the bracket, and if there are multiple complex substituents, we instead use bis, tris, and tetrakis. They are used to refer to multiple complex substituents. For example, say this substituent is there, and basically another one of these substituents is joined to main chain. Like one of these is bond here and another is bond here. So we will say 2,3 bis, name of this complex substituent, butane. Okay, and if there is some di, tri, or tetra here, we are going to consider it as a part of the alphabetical order. But say there's something like sec propyl or sec butyl. Okay, no, sorry, sec propyl does not exist. Say if we are joining sec butyl, so we will not consider sec in alphabetical order, we will consider B only. Okay, same with tert. And say a shorter name is a better priority than a longer name. For example, if there are two substituents, one of them is chloro and another is chloromethyl. So chloro will take the priority because it's shorter. And if their small number is greater than large number, for example, say one substituent is 1 chloroethyl and other is 2 chloroethyl. So 1 chloroethyl is going to take the preference. Okay. Now let's start actually naming the compounds. For alkanes, like simple alkanes with no disturbance in between, like if we are saying alkanes here, we are considering only carbon-carbon compounds with hydrogen, and also basic substituents like halogens are allowed. Other alkyl substituents are allowed, but no functional groups or multiple bonds are allowed. Okay, we are going to name them separately later. So in order to start naming alkanes, we will choose the longest carbon-carbon chain as the parent chain. If there are more than one longest carbon-carbon chains, then we will check for the one with maximum substituents. If you remember, we read something like this. The max number of carbon atoms take priority over the number of substituents. So same thing happens here. If more than one longest chain, check for maximum substituents. And if even the number of substituents is also same, check for the lowest set of substituents. I already explained this to you. Look from what side we get the lowest set for the number of substituents. And if everything fails, go with alphabetical order. Now, I have selected the main chain. From where do I start numbering the main chain? Well, start by checking the lowest set of substituents, because number of carbons will be same either way. You have already selected your main chain. Now the numbering which you do won't affect the number of carbon atoms. Like if I have hexane here, if I start looking from here or here, it does not matter, it will have 6 carbon atoms. So yeah, I have to start by checking the lowest set of substituents, and if both sides give me the same lowest set of substituents, then I have to prioritize the alphabetical order. Now once I have selected the parent chain, how do I start writing? Well, first look for the 2-degree prefix. Write the substituents in alphabetical order with their number of position as the coefficient, like 2-methyl, 3-ethyl. We already talked about this before. This means at second position, second means you have done numbering. So you have written 1, 2, 3 and so on. So at the second position, there is a methyl substituent, and at 3, there is an ethyl substituent. Okay. So, and if both of these are present, you will write 3-ethyl first, because E comes before M in the alphabet. This much I expect you to know, that's LKG knowledge. And it does not, basically ascending or descending number does not matter. You only have to look at the alphabetical order of the substituent, okay? And say what happens if these letters are the same. Well, then you compare the next letter. Then next, what happens if it's like chloro and chloromethyl? Then the first 6 letters are the same. Then as I told you, give priority to the one which is smaller. Okay. So these are some examples. Take a look at these. If you have a doubt, you can question your own existence. Actually, no, you can ask me. But yeah, look at this question. So what happens is, first we identify the main chain. Well, the main chain will have 9 carbon atoms either way, whichever way I look at it, because either this I pick or maybe I pick this. But it's all having 9 carbon atoms. So which one do I pick? Well, you pick the one which has the maximum number of substituents. See, if I pick this as the main chain, it has 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. 10 substituents. But if I pick anything else, it gives me less number of substituents. So this has to be the best carbon parent chain to pick. So once you have picked that, from where do I start numbering? Well, if I start numbering from here, what's the issue? If I write this as 1, 2, 3, 4, 5, 6, 7, 8, 9, what is the issue? Well, look at this. We have, if we do this, we will get the same locants for the substituents. Hence, we now have to look at alphabetical order. This is tri-bromo. Okay, tri-B starts with B. As I told you, tri does not count in alphabetical order. Here, trichloro. Tri does not count in alphabetical order. So, of course, B takes priority over C. And hence, via alphabetical order. Okay, so once you have named the main chain, you now have to start arranging the substituents in alphabetical order. The way I like to do this is, before writing the actual name, you write all the substituents in alphabetical order as a list. So how? You see at 1, at the first position of the numbering, there's a tribromo. How? If we zoom into this, it looks like this. So tribromo. At first positions, there's tribromo. At the 8th position, there's bromo. At 9th position, there's trichloro. And at the 2nd position, there's chloromethyl. And at 4 and 6, there is trichloromethyl. Now let's understand why I have written them like this. Now first I had to separate all the bromo and the chloro, because I know bromo is going to take the top spot. So between bromo and bromomethyl, bromo took the top spot because it's a shorter name, and followed by bromomethyl because B is still higher than all the other C in the alphabetical order. And it shouldn't be hard for you to see why chloro wins over chloromethyl. And for the last dilemma, there's chloromethyl, there is also chloromethyl. Well, then which one do I pick? We don't count tri in alphabetical order. But well, when we look at you know, the length of the name to compare, then this falls behind because it's a longer name. Okay, so then the writing part is very easy. You know the alphabetical order. So whenever there's try, you write the position three times. Okay, so 1 comma 1 tribromo 8. This is a complex substituent. Put parenthesis 8 1 bromomethyl followed by 9 comma 9 comma 9 trichloromethyl. Oh, I forgot. Oh, there is no methyl here, sorry. But why did we write 9 three times? Because there is a tri here. And again, 2 chloromethyl. Why? Because at second position there is a chloromethyl. And it's a complex substituent because extra branching takes place. So 1 chloromethyl, and at fourth and sixth position there are two groups which are trichloromethyls. So 4 comma 6 bis 1 comma 1 trichloromethyl. Why bis? Because I told you for complex substituents we use bis, tris, tetrakis, pentakis, hexakis, heptakis to refer to multiple complex substituents in a carbon chain. Okay, so that's done. Look at this one. We start numbering from here because see, parent chain is same both sides. Two substituents are there. Both sides give the same position to them. So we give priority to 1 chloroethyl over 2 chloroethyl via this rule, and hence the numbering starts from here, and this is the name of the compound. Okay. Now let's look how to name alkenes and alkynes. Now there is a new factor. You will no longer look at the number of carbon atoms first. What you will look at, however, you are going to select the parent chain which has the maximum number of multiple bonds covered. For example, here this is the longest chain, but we don't care. We will pick the one which has maximum double bonds. And now that we have picked the one with maximum number of double bonds, we can now select which way to number it. This way or this way. Well, now we choose this way because this gives a lowest set to the only substituent here. We did not choose this way like 1, 2, 3. We did not do because this would give a set of 3 to the substituent, but this way gives a set of 2. So only after you have selected the main chain with maximum number of multiple bonds, only then you move on to the number of carbon atoms or the number of substituents. Okay. Number according to LSO of multiple bond. If LSO multi bond same both sides. For example, if say there was a, ignore this here. Let's say that there was a triple bond here and you were asked which way do I number it. Well, in that case, you are going to give priority to the double bond in place of the triple bond. So if there was a triple bond here, you would still name it this way. But if the triple bond happened to be here, ignore this, you would name it this way because double bond takes priority over triple bond. Okay. Now, here are a couple examples for you. Look at these and tell me if you have a doubt. Now let's learn how to name monocyclic compounds. How do we name monocyclic compounds? Very easy, trust me. Only 1 degree prefix is added, which is cyclo. Okay, like this is cyclopropane, cyclobutane, cyclopentane. This is cyclohexene because there's a double bond here. So this is cyclohexane. If it was just like this, a benzene without any double bonds, then this would be cyclohexane. Okay. Now, as a general rule, when in one singular compound there are more than, so if there are more than one rings present on an open chain compound, then the open chain is by default taken as the parent. For example, here you can see there are multiple phenyl groups as substituents and phenyl is a ring. So the open chain is taken as parent and we call this triphenylmethane. Triphenylmethane. And there's an H here. Okay. Similarly, you can see there are two things here. Okay. Two rings here. So this will be taken as the parent chain. Which way do I number it? Look at the lowest set of substituents. This will give 2 and 4. But if I draw this way, it gives 1 and 3. So this is by default the parent one. And what do I put forward between cyclohexyl and cyclopentyl? Look at the alphabetical order. H comes before P. Easy. Cyclohexyl comes before cyclopentyl irrespective of the number. And the main chain had 4 carbons, so it is a butane. Now look at this. This is DDT. Okay. What is the IUPAC name of DDT? It's 1, 1, 1 trichloro 2, 2 bis 4 chlorophenyl ethane. How? Look at the main chain. There are multiple rings here, so the open chain must be the main chain. Now, which way do I number it? Do I number this as 1 and this as 2? Or this as 1 and this as 2? Take a moment to think why. And watch. The answer is written right in front of you. Just try to justify. The reason is written right in front of you. Just try to justify why I have written it this way. Well, you idiots, I have numbered it this way because this side has more substituents. This has 3 substituents and this has only 2 substituents. So, 1, 1, 1 trichloro. Well, C. Again, what is the alphabetical order? There's chlorophenyl, there's chloro. Shorter name takes the priority. We use tri for a simple substituent like this. Like, I know I told you simple substituents are alkyl groups, but this is also simple substituent because there is no extra branching here. But this, of course, is a complex substituent, and you would have to name it like this is the radical carbon. Now, this is 1, 2, 3, 4. So 4 chloro benzene, 4 chloro benzene, or you can also call it 4 chlorophenyl if you want. Okay. So 1, 1, 1 trichloro 2, 2 because at second position it's there. Bis because 2 of them are there. 4 chlorophenyl and ethane because the parent chain has 2 carbon atoms. I hope this is easy for you to understand. Okay. Now, if only one ring and one open chain is there, for example, compounds like this, only one ring is there and only one open chain is there. Well, then choose the parent chain according to maximum functional group. I told you functional has most priority. We will learn what those are later. If number of functional groups are same, then choose number of multiple bonds. If those are same, look for number of carbon atoms. And if that is also same, look for number of substituents. If everything is same, give up and take ring as parent. For example, here. Now, you are currently at a point where it is easy for you to write the name. The only issue where students face is selecting the main chain. Writing the name is very easy. Follow alphabetical order, do some more shenanigans, and you have the name. This place where students feel the most pressure on them is when you have to actually when you have to actually number the compound or select the parent chain. So we are going to quickly select the parent chain in every example we have here. If you look at this is parent chain because this has more multiple bonds. Here, which is the parent chain? There is no functional group, there is no substituent, there is no double bond or multiple bond. So this has 3 atoms, but this has 5 atoms. So this must be the parent chain, and cyclopropane must be treated as a substituent. So 1 cyclopropyl pentane. Here you can see 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So this is taken as a side chain because this has more atoms. And you can see it very clearly here. Again, this is main chain because more multiple bonds there. This has equal number of atoms in both the open chain and ring. So by default, the ring is taken as the main chain, and propyl, the open chain, is treated as a substituent. Here again, this is taken as main chain because it is irrespective how many carbon atoms it has because it's straight and has no double bonds. If it had 3 double bonds, then we would take this as main chain. But here, both the double bonds are present in the ring itself. Now I want to give some extra light to this example. How did you number this? Like how? So keep in mind, if you will either number like this or you will either number like this. You won't start numbering like 1, 2. No. Both the atoms of double bond should get lowest locant. So if I had started numbering like this, I would get this substituent at the 3rd position. But this way gives me the substituent at the 2nd position only. No, you cannot start numbering like this because that will violate the set of locant rule for the double bonds. We need to give the lowest ones to the double bonds and to both the atoms. And only once that's done, we give it to the extra substituent. Okay. It's like it's almost like taxing the people of your country and using it to build your own mansions and cars, and what's left is given back to them in minuscule amounts. But I won't get political on this channel. For that, you will have to buy something else. I'm kidding. But yeah, this should be easy for you to understand. This is basically just an illustration of the lowest set of Logan rule. Again, this is called now this is an interesting one. This is a shared double bond. Like I can consider one atom as part of ring and one as part of the open chain. So which one do I consider a substituent? Then again, follow this rule, the number of carbon atoms rule. You can see both of them are single chains except for only this double bond. So here cyclohexane is taken as the main thing because this has lesser atoms. And this entire thing is treated as a substituent, propyl, and connected by double bond, so propylidene. But here this is a shorter ring and this has more carbon atoms. So here this is treated as the substituent and connected by a double bond. So cyclobutyl connected by double. So cyclobutylidene and mention as 6 atoms. So cyclobutylidene hexane. Try naming this compound. The same thing I gave you 2 plus 2 as in class question, and I gave you 337 plus 7 4 6 7 as homework. But yeah, try this one and write the answer in the comments. Now we will learn how to name compounds with functional groups, and this is going to be the last section of this video. So how do you have to make the main chain selection? You select the main chain which has the maximum number of principal functional group. Bhavya, what is this principal functional group? We will know. Don't worry, we will know. So the final priority order is functional group over multiple bonds, over number of carbon atoms, over number of substituents, over lowest set of Fg over Mb over S. You should know the abbreviations by now. And lastly, alphabetical order. So numbering has to be done numbering has to be done according to lowest set of principal functional group. Principal functional group is nothing but the most priority functional group of the entire compound. What is priority here? Well, this is the priority order. Remember this. It is carboxylic acid with sulfonic acid, then anhydride, then ester, then acid halide, then amide, then nitrile, then isonitrile, then aldehyde, ketone, alcohol, thioalcohol, and amine. Now see, the later part is easy to remember. Cyanide over isocyanide, aldehyde over ketone, and group 16 over group 15. But how do I remember the acid derivatives? Just how? Well, if you have ever had pneumonia, you would know that eating cake is not good to heal pneumonia. But if you are non-vegetarian, eggs can actually speed up healing from pneumonia. So cakes suck and eggs heal pneumonia. Cakes suck and anhydride, eggs, ester, heal, halide, pneumonia. From pneumonia, remember N. Okay, they heal pneumonia. This is for acid derivatives. Now let's look back at the rules again. The main chain with maximum principal functional group is selected. For example, if a compound has carboxylic acid, nothing comes above it. Carboxylic acid will be a part of the main chain, and there is no exception, except few. But we'll look at that later. So once this is done, there is a special rule. If the many of these functional groups have a carbon in itself, so if that carbon of principal functional group just so happens to be a part of the main chain, then start numbering from their carbon without asking. We will look at examples. For example, here we saw that we can include carboxylic acid in the main chain. So, without looking at anything else, we start numbering from here. And now, which way do we go? This way or this way? Well, of course, this way, because this has more multiple bonds. Okay. But say instead of carboxylic acid, there was sulfonic acid. So now we cannot start numbering from here. Don't be an idiot. Sulfonic acid is not. Does there look a single carbon to you? Find the carbon. I'll give you 7 years. You won't be able to find a carbon here. So where do I start numbering from? Well, this is a very good priority functional group. I can start it from here. But no, why will I start it from there? I will start it from here because this gives the lowest set to my principal functional group. If I started from here, it would get 4. But from here, it gets 3. So 3 takes the obvious priority and 4 doesn't, because we want the lowest set to be given to the functional group first. Only once all the needs of functional group is met, only then we will move on to multiple bond. Okay? And hence you can read these names here. Now see, this is a table you have to remember. I am sorry. These are the names when a compound looks like this: alkyl group connected to the functional group, and this is what it looks like. Take a moment, pause the video, note this down. I will give you PDF notes. Okay? But see, if a compound has multiple functional groups, for example, say it has both carboxylic acid and alcohol. Now we know, according to this list, carboxylic acid takes the priority. So, without any doubt, if a group takes the priority, it becomes the suffix. For example, we know carboxylic is there, so the compound will end in oic acid, because oic acid is the suffix of carboxylic acid. But for alcohol, which is not a principal functional group anymore, because something of higher priority is present in the molecule. So, for alcohol, we will treat OH group as a substituent, and we are going to use the prefix for it. Prefix, which is hydroxy. As a general rule, if the functional group in question is a principal functional group, then use suffix. And if it's a non-principal functional group, like it's not the highest priority in the entire compound, then use prefix for it. And as another generalization, there can only be one principal functional group in the entire compound. Like, there can be multiple carboxylics in one compound, but my saying is that you cannot say that both carboxylic and sulfonic acids are my principal functional groups in one compound. No, only one of them takes the priority, and that is carboxylic. And sulfonic acid will be treated as a substituent because carboxylic is more prioritized. So if sulfonic is there in the compound, you have to use its prefix. But say carboxylic was not there. So now via priority order, sulfonic acid takes the second spot and we use the suffix sulfonic acid. Understood? Okay. Now let's look at this compound, for example. Here we have both amide group and we have alcohol group. So what is the priority? Along to our priority order, amide takes priority over alcohol. So amide is our principal functional group. And as we learned via this rule, carbon of principal functional group can be made part of the main chain. So we start numbering from here. And now you're confused. Which way do I go? Do I follow lowest set of functional group or do I follow number of carbon atoms? Well, once you have your principal functional group selected, all other functional groups will now be treated as substituents. And you know, substituents are treated like peasants. They are not given rights. They are not given anything. And substituents are now not a priority for you anymore. And you will look at number of carbon atoms. This side has 2, this side has 4. Obvious priority to the one with more carbon atoms, and this is your main chain. This will be written like a substituent. Radical carbon start from 1 here, 2 here. This will be 2 hydroxy ethyl. Okay, 2 like second from the naming of the radical carbon, 2 पे hydroxy. This is ethyl, 2 hydroxy, and it starts from here. Okay, now for ester, it looks confusing, but the name of an ester is alkyl alkanoate. Okay, and which part is the alkyl and which part is the alkanoate? The basic structure of an ester looks like this: RCOOR dash, one alkyl here and one alkyl connected to the oxygen atom, which is connected to a carbonyl group. So the one which is connected to the oxygen atom is the alkyl part, and the one which is connected to the carbonyl directly is the alkanoate part. For example, you can say this one is connected directly to the oxygen, and this is a methyl group. So alkyl alkanoate में you write alkyl as methyl, and this one is connected to the what carbonyl group. So you start numbering from here, okay, because this will be connected as a carbon of the main chain. 1 2 3 4, and at the second position there is a bromo. So 2 bromo butanoate, alkanoate, 2 bromo butanoate, alkyl methyl connected to oxygen is the alkyl group, and the O8 part is the one which is connected directly to the carbonyl group. Okay, for amine and amide we follow special rules. Your main chain will be the longer one. For example, here, like main chain selection has to be done as you do always. If this had double bond, sorry, not this, if this was like C2H5 and there was double bond here, you would select this as main chain, but this has more carbon atoms here, so you select that, and there's only methyl here. So this is propanamine. This part is propanamine because there is 3 carbon atoms and 1 amine attached to the first position. But at the end, there's an extra substituent which is methyl. So you write it as N-methyl propane 1-amine. How? At N, at nitrogen, there is a methyl group. So N-methyl propanamine, propane 1-amine. At first position, there is amine group, and on that amine, nitrogen, there is methyl. Okay. Here you can see at the N, there are 2 substituents, ethyl and methyl. So you write it like N-ethyl, N-methyl, and the main chain was hexane. So hexane 2-amine. Okay. But here we wrote ethyl and methyl separately because they are 2 different groups. But say here we had 2 propyl here, so we will write it like N comma N dipropyl. Okay, just like we write for carbons. And you see this nitrogen is connected to a carbonyl group, so this is actually an amide group, so we call it hexanamide because there are 6 carbon atoms, and this is carbonyl group connected to nitrogen, so this is an amide group. And it just so happens that at the nitrogen of the amide group there are 2 propyl. So this is N comma N dipropyl hexanamide. Okay. Now there is special rules for anhydrides. Anhydrides is basically, this is basic structure of anhydride. This is more generalized. There will be an oxygen atom connected to 2 carbonyl groups like this, and those 2 carbonyl groups will be connected to 2 alkyl groups like this. So for example, say like we have okay, so for example, say this group was methyl. Okay, so don't get trapped. There can be a CH3 here, CH3 also here. But if there is a carbon atom here, so if there are 2 methyl like this here, this is ethane. Don't call it methanoic anhydride because it will be ethanoic anhydride because there are 2 carbons here. But say it's unsymmetrical, like here there is a methyl group and here there's ethyl group. So in totality there's 3 groups here and there's 2 carbon atoms here. So this will be ethanoic propanoic anhydride. If there's unsymmetric, you have to write both the names, and if it's symmetric, only one name is enough. Okay. But what if it's like this? Well, then don't worry. You just have to find, like I have written the reaction here also. Basically, how an anhydride is formed. there will be two carboxylic acids next to each other like this, and one of them will dehydrate, and this bond just moves here. Okay, this just goes away. So this is how this anhydride was formed. Check for yourself. So this carboxylic acid will have a name. It will be hexane 1,2 dioic acid. But just replace acid with anhydride and you will get name of this guy. Okay. Now, for esters and aldehydes, they sometimes show variable prefixes. Now, there are two ways an ester can be connected. This way, like connected via the carbonyl, or this way, connected via the oxygen. Like here, COO is definitely there. That's the sign of ester. But if it's connected via carbonyl or it's connected via oxygen, it has different prefixes based on that. Okay. How? How is it different? Well, if it's connected with carbonyl like this, its prefix will be alkoxycarbonyl. How to remember? You see, this we learnt as OR group. So this is alkoxy and this is carbonyl. So alkoxycarbonyl. At when the ester is connected, if you see the alkoxy group is visible, then don't think, use alkoxycarbonyl as prefix. This is main chain connected like this. So this, so if this is not the principal functional group, you will use alkoxycarbonyl to write its prefix in the IUPAC name of the compound. But if it's connected via the oxygen, you will call it alkanyl oxy. Okay. For example, here we say this is connected via the oxygen. So this group is ethanoyl oxy. Why? Two carbons and connected via oxy. So ethanoyl oxy. And at second position, it's connected via carbonyl and there's only one carbon atom here. So you call it at second position methoxycarbonyl, alkoxycarbonyl. So 4 ethanoyl oxy, 2 methoxycarbonyl hexanoic acid or hexane 1-oic acid. Okay. And for aldehydes, if say main chain is like this, and say their aldehyde carbon, like this is the aldehydic carbon and it's part of the main chain. Okay, so we use the prefix oxo for that. But if it's not part of the main chain, for example, let's say there's a carboxylic acid here and there's another carboxylic acid here, and somewhere in between there is an aldehyde connected like this, so it's not part of the main chain. Well, that's unfortunate. So we are going to use formyl as its prefix. Okay. And lastly, these are some special rules for rings. If a carbon terminating group is directly attached to a ring, we use special prefixes. Look at these prefixes. For COH, it's literally just carboxylic acid. For anhydride, it's carboxylic anhydride. For amide, it's carboxamide. For COX, like acid halide, it's carbonyl halide. For ester, it's carboxylate. For CN, it's carbonitrile, and for CHO, it's carbaldehyde. What am I saying? Like, look at this. If it's like this, we don't count this in main chain. We treat it like a substituent while naming it, like cyclohexane carboxylic acid. Similarly, you can see, but no, actually, this is now a normal compound. Like this was the part of the exception I was talking about, like carbon terminating group. Like this is terminating group and it is directly attached to ring. Then we use special prefix. But here we will not be using special prefix because the terminating part is not connected to the ring. There's a carbon atom in between. So we'll priority to principal functional group and we will start numbering from here. And at second position there is cyclopentyl substituent. Okay, and here you can see again terminating group connected to, directly connected to ring. So aldehyde takes preference and OH will now be a substituent, and over substituent we choose double bond as preference, multiple bond will be given priority. So we start numbering from this part. But we name a number this way because double bond takes priority over a substituent, and at fifth position there is hydroxy group. So 5 hydroxy cyclohex 2 ene carbaldehyde. You understand why? Because at fifth position there is substituent, and this is a cyclohexane ring. And at second position of the cyclohexane ring, there happens to be a double bond, cyclohex-2-ene. And at first position, there is carbaldehyde. If at it as first position, we don't need to write the number, okay? And the same rule applies when you are dealing with open chains with more than one carbon atom. For example, with more than one principal functional groups. For example, if you have like this is butane group, and there's COOH, another COOH, another COOH. So the main chain will be taken as 4 carbon atoms only, okay? And we will name this at first position there is carboxylic acid, at second there's carboxylic acid, and at third there's carboxylic acid. So we will call it 1, 2, 3. Sorry, not like, at this position there is carboxylic acid, so the actual name will be butane, because there's 4 main chain atoms, butane, 1, 2, 3, tri, and that special prefix from earlier, tricarboxylic acid. Same applies for open chain with more than one carbon atoms. What am I saying? More than one principal functional groups, like this. At first, second and third position, the carboxylic groups are there, so main chain you write, and at those positions you add tricarboxylic acid, okay, which was the special prefix from earlier. So well, that was it. That was entire IUPAC nomenclature revised for you at advanced level in very few time. And we will soon make another video in which we will be covering all the common names. But for now, this should be enough for you to start solving PYQs if you have listened to everything properly. And I will soon give you the notes in description and pinned comment. Thank you for sticking by. And again, it's been 6-7 minutes. So thank you.